Welcome to UVU CS3060 Lecture 9.3, where we discuss contiguous memory allocation. Now, contiguous memory allocation is a type of allocation scheme that is handled by the operating system, where we have main memory support for this particular allocation scheme. Now, remember that memory is a limited resource. Memory is not nearly as plentiful a storage device. It's usually more expensive. So we need to find a way to allocate this memory efficiently for processes. One of the early allocation schemes was called contiguous memory allocation. It's not used very frequently these days, but we'll start here. Main memory is usually found in two partitions. One partition will hold the operating system, and this is usually a low memory where we'll also find the interrupt vector. So the operating system is loaded near the interrupt vector in low memory. The other partitions are user processes, and those are kept in high memory. Each process is contained within a single contiguous section of memory, meaning that, and contiguous, this is an important term, means unbroken. So a process, from its start address to its end address, does not have anything in between, like other processes or operating system data. Now, we use the relocation registers to protect user processes from each other. Now, this is fairly easy to manage. We keep in the base register the smallest physical address for that particular process, a limit register containing the range, how much space is taken up, and we use the memory management unit to map those logical addresses dynamically. And one of the nice things about this is the base register is actually containing the physical address, but the program itself doesn't need to know what its physical address is. Thus, we have logical addresses for processes. And the memory access happens by performing first, we take the logical address. Remember, this a logical address that's generated by the CPU in a contiguous address scheme starts at 0. And the largest address can be the size of the program or the size of the memory allocated for that process. First, that address is checked against a limit register. The limit register determines whether the address access, the logical address access, exceeds the boundaries of the process. If it's not less than the limit register, then the operating system is informed and the process is dealt with appropriately. If the logical address is less than the limit address, then the relocation register is added to the logical address, and immediately we have the physical address. First thing to note, all of this happens within the memory management unit. Second thing to note, this is different than the way we saw the base and limit registers used before. In base and limit, we saw a comparison to the base, but now we're using a relocation register to add to the address. Now, if you remember, that comparison to base was to check to make sure our logical address was not less than our particular base, but we don't need to do that now. So there really is no instance where a particular logical address can be too low. Logical addresses can start at 0 and move up from there. Adding the relocation register takes care of that lower bound. All we need to be concerned with is the upper bound. Now, multi-partition allocation allows us to put processes into various partitions, variable size partitions, depending on the needs of the processes. So if we take a look here, we have an example of a system state with 3 processes loaded. Process 5, process 8, and process 2. Now let's say process 8 either terminates or is swapped out. When that memory is freed up, either by termination or swapping, that leaves what is called a hole, which is a block of available memory. That block of available memory can be used by new processes or swapped in processes. So here we have process 9 that's being loaded in, as well as process 10 that's being loaded in with this particular hole here. So one of the things that we need to be concerned with is how do we keep track of these process partitions. Well, this is something the operating system manages, usually through a partition table for main memory. And it keeps track of which processes have which partition and where the holes are located, so a process can be allocated for that. Now, how do we decide where a process is going to go? Well, there's several ways to do that. If we consider the a hole where a process could go, we might have a first fit algorithm. This first fit will find the first hole that's big enough for a particular process. Now, in that particular case, this is very fast, but may be inefficient. The processes, as they're loaded, may end up leaving small holes that are spread across the system. If we go back to our previous diagram, consider for a moment that process 9 might be freed up here, leaving a hole where process 9 was, and then this hole after process 10. This leaves enough memory for some process to be loaded, but not enough space within the hole to load an entire process. Perhaps it would have been better to have moved these processes around or loaded them in a different order. In a best fit allocation, the entire list of holes are searched for the smallest possible hole for a particular process. Thus, it will produce the smallest leftover hole. This could be problematic because then you end up with very, very tiny holes, and if there are a lot of these tiny holes, memory holes, it can actually leave a system unusable. Worst fit, on the other hand, tries to find the largest hole. So it goes through the entire list again and checks to find the largest hole to use, which guarantees that you're going to produce the largest leftover hole. The thing is, first fit and best fit tend to work better than worst fit. So the best fit and first fit will be the algorithm that is most commonly used in a contiguous memory allocation scheme. Now, we discussed holes being broken up between processes and possibly being too small to be usable. Anytime there is enough memory to allocate for a process, but it's broken up into holes that are too small for that process, we call this external fragmentation. So if we go back to our previous diagram, when process 9 exits or swapped out, the hole that is left behind, as well as this hole right here, is considered external fragmentation. External fragmentation is memory fragmentation that happens outside of the process's memory allocation space. So here we don't have any external fragmentation. It's one contiguous freed unit. But if process 9 were freed up and two holes were broken up, divided by process 10, these two holes would be considered external fragmentation. The alternate to that is called internal fragmentation. Internal fragmentation is where a block is allocated for a process that is larger than what the process needs, which means the process is only going to need, say, 5 kilobytes. But the operating system has allocated 8 kilobytes for that particular process. The process is never going to exceed 5 kilobytes. That's what it thinks that's what it needed. That's all it's going to attempt to use. So If 8 kilobytes is allocated for that 5 kilobyte process, there are 3 kilobytes that are unused within that particular partition. We call that unused space internal fragmentation. Internal fragmentation does not usually happen in a contiguous allocation. But when it comes to first fit, if we are allocating blocks, first fit will show that we lose about half of the blocks to some sort of fragmentation, usually external fragmentation. How can we get rid of fragmentation? Well, one way we can do that is through compaction. If we go back to this diagram, where process 9 is freed up, compaction is where process 10 is either moved to the beginning of this or is moved to the end of this free block, giving us a contiguous free block to work with. Compaction is actually very, very slow. We actually have to lock memory from access as we move this process or these processes around in memory. And we also have the problem with I/O, so we end up having to do double buffering. One thing to be concerned with as well, we're talking about fragmentation within memory, but fragmentation can also happen within the backing store. And we need to somehow mitigate that, usually through compaction. This brings us to an end for lecture 9.3, where we talk about contiguous memory allocation.